So we don't actually have a date for the midterm set. When do you guys want the midterm?
What would it be midterm?
Well, we need a midterm because the university gets all upset if I try and make it an 80% final, and I think that's unfair to the students. So I need a midterm evaluation. So normally the midterm would be on the material up to the stuff we study about a week before the midterm. So we can do it what I recommend is we take, it would be a sort of a 3-hour midterm. It's based on, I'll make sure we're clear on the assignments. I wouldn't have it the week after reading week. I would do it the week after that. So the goal would be that the midterm would basically cover the material up to today's lecture. And I'd suggest we do it the Monday morning on October. I need to open my calendar. So today is the 6th. Here, I can share my screen. Today is the 6th. Our next class is the 18th because we have the week of the 10th off. And I suggest we do the midterm, we could do the Monday the 25th. So starting at 8:30 and going till, I guess 11:30. Do any of you guys have conflicts?
I think I'm fine.
Apurvi, do you have conflicts with your classes? Do you have a class right after this?
No, that would be okay.
That'll be okay. Okay.
What time did you say?
Well, it would start at this time, like class time, and it would go for 3 hours.
That would be okay.
Okay. And so I think that's what I'll do is I'm gonna book it for (8:30 to 11:30 Eastern). Open book based on the assignments. Very slight variation of the questions from the assignments. That'll be the midterm. I'll send out an announcement for everyone who's not here, so they'll get an email, and that's the official written doc way of doing it. So it'll be up to today's lecture or so. Because you'll get reading week then to catch up on all the, and I'll indicate, I'll send out an email probably early next week, maybe on the weekend or Monday or Tuesday, which assignment questions are valid, because they're kind of covered by the stuff we've covered up to this point. And I might modify a couple of assignment questions because we skipped a few things to move a little bit faster this year. Okay. I am going to go from here. So last class, I made a mistake in my final slide because I was tired. I indicated that DMDO formed epoxides from the top face. This is incorrect. It forms epoxides from the bottom face. Correction. We got confused. So both MCPBA and DMDO always attack from the bottom face. And I really don't know how, I don't know how I made this mistake. I know better. I've done this reaction.
I was thinking of that because I thought the bottom face was less,
It is.
blocked.
I don't know what the hell I was thinking. I was getting confused with something else, and I'm really sorry. But I make mistakes. So mea culpa. I'm very, very sorry, and I apologize for any confusion that'll cause. I'll highlight that also in the announcement, the midterm, that I did make a mistake in the notes and that those should be revisited in case somebody misses this. Because I think a lot of people are watching these after the fact. I hope they're watching them after the fact. I have no idea. Okay, so what I want to do is continue talking about glycals and some of the flexibility because that this system has. So these epoxides are all good and all. And I kind of rushed to get to them. I don't know why I rushed so much last class. I want to discuss a few other ways. Well, I guess the thing is here, we've seen some very simple ways to introduce diols, and we did it with both MCPA or DMDO. But the thing about glycals is that they're very, very flexible in what you can do, and that's because you can make them in different ways. So for right now, we've made the sort of the 2-deoxyglycal. Like we've already removed the OH. And that makes sense because we're putting the OH back. So far, we've done reactions on it which add oxygens to both sides, to epoxides. But we have ways of doing this kind of chemistry without removing that OH. So even using the same starting material we used last time, so we use this bromoacetate, and what we did last time was we treated that with zinc metal, and it attacked the bromine, and then we generated the glycal by kicking out the acetate. But if we do something slightly different, I like this because it ties in with some stuff we talked about a little bit earlier in the course. We use one equivalent of catalytic tetrabutyl ammonium bromide, one equivalent of, the name is escaping me, lutidine. One equivalent of collidine. That's this thing, it's trimethylpyridine. And ethanol, we get a different product. So I think this was actually probably discovered by mistake because I think what they were trying to do was add ethanol as a glycosylation agent. That's not what they got. So any idea about how this might proceed? What the first step might be? We've already seen it with the same reagent.
The catalyst kick off the bromine.
And do what?
Do what? It donates its electrons to the anomeric carbon and kick off the bromine.
And so what happened? What's out the anomeric carbon then? Because you said the catalyst, right?
Yeah.
I agree with you.
Yes.
I agree with you. So what's at the anomeric carbon now after it's done that?
It's nitrogen.
Nope. So remember what this is. Tetrabutyl ammonium bromide is nitrogen with 4 butyl groups. Positively charged, Br minus.
To do that.
So nitrogen doesn't have any electrons to give.
Oh
Yeah.
wait, it's the opposite. Bromine?
Yeah, you get a better bromide.
Ah,
So we've seen this before. This is how you make the beta bromide, and it's very reactive. And so with the beta bromide and a C2, when I made beta bromides back there, we always never had a C2 acetate. I was really careful not to. Because if I have a C2 acetate and a beta bromide, very, very fast. Because it's just perfectly aligned. The bromide is a really good leaving group. And we make this. So one thing that can happen, and it doesn't, I don't fully understand why, is ethanol could come in as a nucleophile and attack beta. And if you drew that, I think it would be reasonable. It's just, it's not what happens. What happens instead, and I think it's because there's a little bit of collidine present, and so it doesn't deprotonate the ethanol, but it weakens the ethanol, the OH bond on the ethanol. And so the ethanol can come in and bond there. I'm just going to move this acetate over a bit. Okay. Sure. Now I think the thing we need to think about is this is probably in equilibrium. Not probably. Is in equilibrium with this. You know, that it's just nothing in oxocarbenium likes doing more than forming. And so it's not a resonance structure. I'm breaking a bond, but it's kind of, we just need to remember that, yeah, an equilibrium lies towards the starting materials, like it lies towards the stable thing, of course. But that bond is weakened. And so one other thing that can happen is instead of using the lone pair on the oxygen, and this is what does happen because it's irreversible, is we have a hydrogen there axial at C2. We have a rather pathetic base in the form of collidine. It can deprotonate. And kick that out. And what does that do? So these are the purple arrows. Well, that generates the glycal. We get a tetrahedral intermediate. And if you remember, carbon does not like making three single bonds to oxygen. It wants to make a double bond and a single bond. And so it kicks that out. And I am out of page on my space on my slide. Continued. I'm not going to try and just put it on the same slide. So I'll just redraw what I had there. Should probably do that more often. I'm used to writing on blackboards, and I haven't really adjusted to writing on one of these slides yet. And I really should. I've been doing this for like 2 years now. You think I would have adjusted, but I always get surprised at how little space there is. So I apologize for that. So we have a case here where we have a glycal, but the C2 oxygen is still present. So with the zinc reaction, we lost the C2 oxygen. With this one, we still have the C2 oxygen, which is kind of neat. And I don't think I finished talking about sulfides. I don't think I finished talking about sulfoxides and sulfones. Like, I must have gotten distracted. I guess I'll have to go back to those later. Shit, I think I got off on protecting groups midway through and I didn't go back. Another way we can make these is from the glycosyl sulfoxide. Yeah, actually, normally these will be benzyl protecting groups at this point. Just the way you make sulfoxides, they almost always are. You can go out of your way and do that. So if I have a glycosyl sulfoxide, and this is a relatively easy molecule to access, if I just heat that, you make a 5-membered ring there, 1, 2, 3, 4, 5. That then breaks the carbon-hydrogen bond, regenerating a double bond, kicking out a sulfur. This is actually a very normal reactivity pattern for sulfoxides, like general sulfoxide sugars are not. It's a really good elimination mechanism. And again, note that we retain the C2 hydroxyl this way. So I think these are the 3 best ways to do it. And if you note, we have 3 different strategies. The first one with just the zinc that we talked about last class, the zinc and the glycosyl bromide, generates double bond with nothing at C2. The first one we did with this common starting material generates the glycal with an acetate at C2, so we have that base sensitive protecting group. It's very easy to make. But if we want a more stable protecting group, we can use the glycosyl sulfoxide, which will generally give us a benzyl group. There are other groups you can get there, but they're kind of a pain in the ass. It works best with benzyls. So we can sort of access these glycals in different ways. Now, if I take one of these glycals that we just did, one of the ones with the C2 still present. So I don't know, let's take the acetate one. And I treat that with DMDO. I get something a little interesting. This here is pseudoaxial, so this is pseudoequatorial. And then if I treat this with a nucleophile, and the nucleophile I'm going to start using a little bit in this class is sodium azide. And just remember what the Lewis structure of sodium azide is, and then we'll talk about why we're choosing this. So azide is -1. I'm just moving you are viewing my screen over. This is going to come in and attack and displace. Now this isn't particularly useful. We've attached an azide at C1. It is useful for all sorts of bioorthogonal chemistry that we're going to get to near the latter part of the course. Because you can do all sorts of cool click chemistry with it. But now I've got a C2 sugar that has 2 oxygens attached to it. And I can say with absolute certainty that there is no natural sugar, any natural product with a sugar in it, that has a carbon with 2 single bonds to oxygen on it. It just doesn't exist in nature. So I'm going to circle that. I tried to circle and no, I tried to change color. Motif does not exist. Now, there's no reason you don't do it, because, you know, messing with things that don't exist is, I guess, what chemistry is all about. But it's of limited utility depending what you're trying to do. I don't know if any of you caught it this morning. The Nobel Prize in Chemistry was awarded to List and Macmillan for organocatalysis, and we're going to actually do a little bit of organocatalysis later in the course. It is that was a complete non sequitur. It has no association with anything else. Just the way my brain was going, because I was really hoping I was going to be awarded for bioconjugation. Then I'm waiting for it to be awarded for bioconjugation, and then I can, if I'm teaching this course, I can start talking about click chemistry and why it won a Nobel Prize today. But it didn't win a Nobel Prize today, so I'll have to wait till next year. But that's okay. I am patient. I have this huge scientific crush on one of the people who should be winning for bioconjugation. She's done absolutely incredible work. And we're going to talk about her work later because it's completely changed how everything gets done with in-cell and in-animal kind of labeling and things, which is just freaking cool. Anyways, so this is kind of useless. But where these C2 hydroxyl groups come in handy is if we want to mess around with some of the chemistry at the other center. So let's take that. I'll show you what I mean by those words I just said. So we take that glycal and we treat that with NIS. We saw NIS earlier when we were talking about glycosyl sulfides. This is, I'm going to draw it in brackets down here. It's the same thing. This is NIS. What we're finding is that, you know, we'll do something completely different, and then we'll see that everyone's using the same reagent. I think it's because carbohydrate chemists have absolutely zero imagination, and so they keep using the same thing over and over again because it's what they've got in their lab, and they try it out and it works and they go good enough, and they move on. So it's a source of electrophilic iodine. So there's the arrow. In this case, I am sure the iodine is on the top face. What did I just do? There we go. You can use NIS. You can use MBS, which is the same thing with bromine. It does exactly the same thing. Top face, very selective. And this, of course, is in equilibrium with that. Okay. So then if we treat this with a nucleophile, it's going to come from the bottom face. So this is useful because all of the, and I'll just draw this arrow in a different color because it's a bit confusing the way I did it. So all of the epoxides, and we're going to return to those in a moment, favor forming the epoxide on the bottom face. So you can never get the nucleophile coming in from the bottom. The nucleophile always comes in from the side, equatorial. But now with the NIS thing, we can bring it in from the bottom. So this is a useful way to bypass that problem. Now, of course, the problem is we have a freaking iodine on there and we don't necessarily want that iodine. There's a few things we can do that are kind of useful with that. And I just want to touch on them. So the first one is we just get rid of it. This, I guess this isn't as useful. So let's say we just did all the chemistry we just talked about. We have a nucleophile. I can now treat this tritin butyl hydride, some sort of radical initiator, and heat. If you don't know the mechanism for this, I suggest you look it up. Actually might be in the notes that I've posted. The overall idea is that we generate a radical at that carbon center, abstract the iodine, and then that radical steals the hydrogen from the tributyl hydride to put the hydrogen back. Look up this mechanism. I suggest when I say look up a mechanism that you look up a mechanism. It's probably a good idea. Okay. So we incorporate the hydrogen, and I'm just going to highlight where that hydrogen comes from. It's this one here. So we replace it. Okay, that's fine. Seemed an awful lot of work to stick a nucleophile in alpha, but if what we're noticing here, and you should notice this, is I have an alpha nucleophile and I have a C2 acetate. That is really hard to do, right? Because all the chemistry we've seen so far with C2 acetate, well, almost all the chemistry, one exception with the bromides, but all the other chemistry we've seen so far, if you have a C2 acetate, you have anchiomeric assistance, you're going to have a beta nucleophile because you're going to generate the oxocarbenium. The acetate's going to share its electrons. It's going to block the alpha face. You're going to get an SN2-like reaction from the beta side. If that last statement confused you, please go back and see one of the early lectures that we were looking at on this because we covered that in detail. So this is cool. Alpha nucleophile with C2 acetate. This is one of the only ways to do it. But this is kind of a boring thing to do with that thing. So other stuff we can do, I think it gets more useful if, again, we can do lots of different types of chemistry here. But the other one I really want to focus on with when you have a C2 substituent is, okay, let's say we have this. Just make that. Let's say I treat this with sodium methoxide in methanol. Okay, so ignore the iodide for a second. What is that going to do? Going back to our protecting group lecture. So we talked about acetate protecting groups, and we talked about sodium methoxide and methanol. I really hate these remote lectures. I'm so sorry that this is your experience with everything right now. This just sucks. Because I don't think things go in as well. I think we're all distracted. So what this does is it removes the acetate groups. This is the standard deprotection conditions for acetates. I find it slightly concerning that no one stepped in with that. Okay. We're going to pretend a nucleophile is perfectly stable. It's not ever going to do anything under these conditions. Have I drawn, again, the OHs or whatever they are doing over the rest of the molecule, they don't matter. If they mattered, I would have drawn them in. Is this molecule I've drawn stable? Do I think that I can isolate this and put this in a bottle long term and it's not going to do anything?
Not really, not quite
No, it's not
stable.
stable. What do you expect to happen?
The iodine come off.
Yeah. What's going to get rid of the iodine? How is it going to come off? I agree with you 100%.
Takes at least 2 equivalents of sugar.
Nope, one equivalent's enough, just what we've got. So remember, I've drawn this, but let's say there's a little bit of sodium methoxide still floating around. We're not done. It's going to happen under these conditions. I should probably put this in brackets.
Oh, so my methoxy?
Yeah,
Like
what
attacks
about it?
back at C2.
Okay,
iodine.
so yes is possible. So you're saying an SN2 reaction, right?
Oh, yeah, I see. That's yeah. Nope.
I don't love the SN2 on a trisub on like that substitute, right? Because normally you need a
Me
secondary
neither.
primary. Yeah, no, I do. What's faster than an SN2 reaction? What's the fastest type of reaction?
That's someone.
Just in the world, like generally, what is always the fastest type of reaction if it's two molecules interacting? As a class, acid-base reactions. Acid-base reactions are so much faster than anything else. And that's because acid-base reactions normally involve taking a proton away from something. And protons are normally on the surface of molecules. And so it's very easy to access the surface of a molecule. So I'm going to say that an acid-base reaction is what occurs here. And sodium methoxide is a damn good base.
So it depronates the hydroxyl group.
Perfect. I agree with you completely. Okay, so we get that. So I'm going to redraw to make the notes make some sense. I'm going to redraw it like that. And if I've got that, what could happen?
The reaction goes back to carbon, right? Carbon oxygen double bond, and then kick off the iodide. I still don't know how to call it at this point.
I would say iodide. I'd accept either, because iodine would be you're talking about the atom, and I buy that. Like iodine means both the iodine atom and I2. Iodide is I minus. I would accept either iodide or iodine, because anyone who cares that much about naming has got too much time on their hands.
Okay.
Technically, I think you're kicking off the iodide, but it's the same thing. Okay, so we generated a carbonyl, we generated a ketone. Okay, we're going to come back to why that ketone is really, really, really important when we start talking about nitrogen at C2. This is a way to introduce nitrogen. Why is that important? Holy shit, nitrogen is everywhere in so much of this sugar chemistry kind of stuff. And in biomaterials, chitosan is basically, and chitin have a C2A nitrogen. It's showing up in all sorts of cell signaling pathways. I'd say C2 nitrogens are probably the most important functionality that they're out there. I'm also just fascinated by them, so I'm really biased. Okay, so I think, like, yes, then you can, if you're careful enough, and let's say you had a benzyl group at C2, which is really stable, you could go through and do SN2s on that center. It's just you'd have to be very careful. But in this case, we had an OH and we had two, and carbon does not like making two bonds to heteroatoms if it can make a double bond to a heteroatom. Like carbon does not want to make two single bonds to oxygen, it wants to make a double bond to oxygen. Or a single bond to iodine, a single bond to oxygen wants to make a double bond to oxygen. So this is all thermodynamically very favorable. But if for some reason you wanted to create some screwed up sugar with two oxygens or an oxygen and a nitrogen at C2, you could by doing SN2s on this with the right protecting group. That's weird and unusual and not really a focus. So what I want to sort of think about instead is going back to our friend the glycal, my friend the glycal. I might be alone on this. We'll use MBS this time just for shits and giggles. We'll change the solvent to ether because it doesn't really matter what you do. This works. And we get the bromide up here. Now this time I'm using something that does not have a C2 position, a C2OH. So I made this probably with the zinc process. And if I do that, it's a little trickier. It's possible it's a little bit trickier, so we'll stick with the acetates. So we've got this. Let's say we then add our favorite nucleophile. I don't know. Let's use a sugar this time just to show that this is fully doable. I don't know. I'll leave it as an exercise from our protecting group. From our protecting group lecture, you should be able to make this guy. And normally there'll be a very, very weak base in here too, because we'll need something to scoop up that hydrogen when we're done. Anyway, so all of this will give us the product. So we get that. Okay, hopefully no issues with that arrow. Now we've got a C2 bromide and no OH there. So one thing I could do is I can burn off that bromide again using tributyl tin hydride and AIBN as we did, and then we would make a C2 deoxy sugar, like just a CH2 there. Again, C2 deoxy sugars, important derivatives, and this is a good way to make them. But let's say I wanted to introduce something more interesting there. I could add in an oxygen. Strangely enough, and this still confuses me, the easiest way to do that isn't to use like water or something, is to use sodium acetate. The problem with water or hydroxide or something is you favor E2s, and so you might start making glycals. Of course, you make a glycal between, just because antiperiplanar, you would make a glycal between 2 and 3, not between 1 and 2 because you can't do it. So weak base. Okay, nucleophile. So one thing that could happen is this can react with this to give. I'm just going to call the other thing sugar. So we're able to use the glycal to go through this really good bromonium ion. Very stable, very nice. It's not quite an oxocarbenium, so your yields tend to be better because you do tend to suppress outside reactions. That's why the glycals are so popular. And again, what we've done here is we've generated this alpha with C2 acetate, which is hard to do. But we've kind of done it ass backwards, right? Like we're always trying to generate the glycosyl bond in the presence of the C2 group. Here what we did is we generated the glycosyl bond, then introduced the C2 acetate. So this is kind of a neat way around the problem. A second really relevant solution to this, something that we probably want to use a lot. Again, sodium azide, I said it would be coming back. This now, Hazel wanted to do an SN2 on a previous example. I like it more on this now because I've replaced an OH with a hydrogen, which is small. So nothing stopping the SN2, which is what we're doing down here too. This is also an SN2. And what we've just done is we have inserted a C2 azide. I don't think we ever tried this with the TN antigen.
No, we use glycal, the double bond one, with sodium nitrogen to get the nitrate sugar.
Yeah, we
Nitrate
did
and
use it. We did go
azide.
through a glycal, right? Then we made the.
Yeah.
I wonder if what we should, maybe this is worth a try. I don't know. It's worked for me in the past when I've done stuff like this. So I have done this chemistry. It worked okay. I imagine it doesn't work very well because if it did, other people would do it. There must be a reason it doesn't work. I can't think of one though. Because all we need to do is replace the. I use a sugar here, but we could just use serine, and it should be fine. I don't know if you have some, and that nitrate chemistry shit is pretty awful. So
It's just horrible.
this might actually be cleaner. If you want to play around with this later. Second generation synthesis. Normally this is really clean because it's all very stereospecific. There's no, you can't get the other anomer really. And the only real risk would be would the sodium azide start doing something wacky with our serine. I don't think so. I think it'll be fine. Okay, maybe we'll talk about this after class, Hazel.
Yeah.
I'm not sure what. This is why I like this class, because I start getting ideas on how I should do my own chemistry better. I had an entire project start because I do one of these lectures and go, oh shit, that's not going to work. Something we're doing in the lab. So what we had then with the epoxides is we had attack from the bottom. With the NIS and the NBS, we have attack from the top. It would be nice if we had that NIS, NBS stuff with attack from the bottom. We're able to introduce that because with the epoxides, we have no flexibility. It's always from the bottom. With the halogens, this looks like it's always from the top, but that's not true. We actually have a different reagent that we can use to get bottom halogens. And the reagent's called IDCP. What is that? It's a weird ass reagent. Which apparently I can't draw to save my life. So collidine again, we just saw this guy. And it's kind of like it's sort of a sandwich where the iodine, an I plus ion, is sandwiched between two collidines. And then there's a perchlorate ion, which is about as non-coordinating as you can get. Like perchlorate just doesn't bind. It just kind of sits there and ignores everything else that's going on. La, 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 la. And so we're kind of holding this iodine in there by dipole interactions with the collidines. You know, if I drew that with a metal in there, you go, yeah, okay, there's a metal between two nitrogen ligands, it's fine. But I find this kind of upsetting. I don't love seeing this reagent. This is a very, very hot iodine electrophile. And unsurprisingly, unlike NIS and NBS, it's big. Because, look, there's two freaking collidines there. So, it's not coming from the top face. It's going to come from the bottom face, even though stereoelectronically it favors the top. I don't want to get into why, but we're going to get the bottom one. Now, nothing else is different. We do all the same kind of chemistry we just did. This is, of course, in equilibrium. With the oxocarbenium. Just so we keep track that the iodine's on the bottom. And so when you treat this with a nucleophile, sugar or whatever, it's going to come in from the beta face because the alpha face is kind of blocked by the iodine. So even if I draw it as the oxocarbenium, we have to remember this is an equilibrium. And so the nucleophile comes in beta. Okay, why? Sure, fine, whatever. why this is relevant and why this is important is if I treat this with sodium acetate, I get the Cis Mannose form, and this is really hard to make. Again, if I think when we went back and we talked about mannose, we said mannose was a pain in the ass because, you know, for glucose or galactose, you can use the antiomeric effect to get beta and the anomeric effect to get alpha. For mannose, the antiomeric effect and the anomeric effect both give you alpha. Beta is really hard to get with mannose, and top phase is sterically hindered, so it's even harder to get. Whereas here, this is kind of, again, what we're using is we're doing glycals to kind of do end runs around limitations in carbohydrate chemistry, because we basically we're cheating at the C2 position. And this allows us to get the beta nucleophile in there. So these glycals, if you want, you can create a cheat sheet from everything we've gone through. And again, part of the exercise of the course is doing that. But what you'll be able to find is you're really able to tune the stereochemistry at C2 and C1 using glycals. You kind of get the inversion of what you get using almost any other thing, which is really kind of handy. One of the other really useful things about glycals is the way you do these kinds of activations. So the last thing I want to talk about with glycals, before apparently I return to glycosyl sulfides to finish discussing those, is let's say I have, okay, no, do this one. I treat this with, let's do IDCP. Doesn't matter, could have been NIS. But I use one equivalent. I let that stir. Okay, this is just what we were just drawing. And then let's say my nucleophile is another glycal. Now, with almost any other conditions, any other type of activating group, we have to be really careful if our nucleophile is the same kind of anomeric activation strategy as the electrophile, because in a lot of cases we're using strong Lewis acids, and they're going to start activating everything in sight. But here we've made a covalent bond, like we've consumed it, we've kind of pre-activated. Don't need to worry about messing with this guy here. So this is just nice and clean. Of course, I could have used an epoxide instead, and you can isolate the epoxides so they're really clean. What I mean by that is you don't have to worry about anything happening to this glycal. And then what I can do is I can do IDCP again, repeat, and I can start making a controlled polymer or oligomer. this is kind of obvious that this works, and it kind of pisses me off that occasionally I'll see a paper come out in one of the really high-end chemistry journals where they basically do this and say, hey, look, we made a new polymer out of this, and everyone loses their mind because they made a single molecule through doing this in one pot, because you can actually do this in one reaction vessel. Like you take your glycal, you add one equivalent of IDCP, you stir for 20 minutes, you add your next glycal, you stir for 20 minutes, you add IDCP, another equivalent of IDCP, and you activate the new one. You stir for 20 minutes, you add the next glycal, you stir for 20 minutes. You never need to even take it out of the flask, and you can start building these long oligomers. And everyone loses their shit going, isn't this amazing? And it's cool, I'll give it that, but it's not amazing. Like it does exactly this chemistry that's been established for 25 years. And I'm bitter that other people are able to get this kind of shit into high impact journals, and I can't be, and I haven't tried. So yes, I think this is more about me and myself than it is about the actual chemistry. The chemistry works really, really well. It's just, we know it works really, really well. Very robust chemistry. It actually got called a cassette approach to making, when cassettes were really cool technology. A cassette approach to making these kinds of things, because you could just kind of click them in one after the other, and you can just build them modularly. So everyone got really excited about that. The problem is you are a little bit limited with what else you can have going on in the rest of your sugar. And it's most useful when you don't need to modify anything else. I don't think I have a lot else I want to talk about glycals for. So we've talked about glycals with IDCP. We've talked about glycals with, in the notes, I have a detailed stereoelectronic discussion on exactly why you get IDCP from one side and NIS from another, but I think we'll leave it. So I don't think there's much more, but I do want to return to sulfides briefly. And what I want to return with that was, we were talking about these glycosyl sulfides before I got distracted by protecting groups. And I think at one point we were discussing right before the end that we could oxidize this and we could get the sulfoxide, which we just saw do something cool to make a glycal. And if we oxidize further, we can get the sulfone. Okay, so why does this matter? Because what we can do is, I want to talk about a few really key concepts here on how we can activate these things and play with it. So if we remember, to activate this, we needed NIS and triflic acid. Now we've seen it. Another good conditions for doing this, unsurprisingly, is IDCP that we just saw. The reason we don't need an acid there is because NIS isn't all that electrophilic. Like you have an Ni bond, it's a covalent bond. The I plus isn't super reactive. And that's why you need an acid to activate the NIS and make it even better, because the sulfur is not a great nucleophile. IDCP, it's an I plus. It is a freaking I plus. It is a reactive I plus. You can stick it on a sulfur. As soon as you have the Si bond, you make the oxocarbenium. Okay. Harsh, okay-ish, but reactive. You got to be careful what else you have going on in your system, because IDCP is just going to add iodine to things. So what's good is if we have a slightly gentler set of conditions. And so we can oxidize to the sulfoxide. And what I often mean by that is MCPBA is the standard way of doing this. Now, you can draw a resonance structure of the sulfoxide. Like this. And as organic chemist, you're thinking, why the hell would I not draw it as that bottom structure? I don't have any charges. That looks a lot more stable. Sulfur's a weird duck, is all I can say. And it exists a lot more like the top form. It actually exists so much like the top form that although it's accurate to think about that bond being pretty strong, a little bit of double bond character, you actually get two diastereomers because you can imagine that there is a lone pair also on a sulfur still. And that lone pair and oxygen actually sit in a tetrahedron, and that tetrahedron is stable. You can actually isolate the two diastereomers or epimers at that sulfur center. This still blows my mind. Whenever you make, if you ever make a sulfoxide, you will see diastereomers. And you will freak out and you think, why isn't my stuff pure? Why do I have two compounds present here? You don't. You just have, well, you do, but what you have is you have that OH sit, or that oxygen on a sulfur sitting at one or the other positions. And a lot of them are actually stable. You can actually purify them by column chromatography, and they are stable at room temperature. If you heat them up to about 150 degrees, they interconvert. Okay, so that's interesting. Why can I use this? Well, I can use a much weaker activating group. So I can activate this with triflic anhydride and normally a little bit of collidine again. The reason we like collidine, I want to look it up. It's called collidine. It is no clearer. Hindered weak base. It's not going to suddenly react with an oxocarbenium and make a new nitrogen carbon bond. It's just going to strip off any extra protons lying around. And that's because this mechanism, in the presence of a nucleophile, like ethanol, and let's do this reaction in acetonitrile. We're gonna generate an oxocarbenium. Plus that. So we've triflated the oxygen. And we're going to have an OTF. If you need to draw the mechanism, you probably should. Remember what OTF is: oxygen, sulfur, sulfur. It's the anhydride of triflic acid. this guy, once we add in our ethanol nucleophile, remember we're in acetonitrile. So do I expect the ethanol to come in alpha or beta if I'm in acetonitrile and I've got no C2 participation? Expected to be beta because of the acetonitrile effect, as we discussed. And we're also going to generate H plus that came from the ethanol. We have OTF minus, so we're going to get a little bit of triflic acid. Which is really destructive of everything, which is why we've added this little bit of base to scoop that up and destroy it. Otherwise, the triflic acid will destroy everything in sight and you will not get a molecule out of it. So with the sulfoxide, we're able to use a weaker, this triflic anhydride, which is slightly weaker than the NIS triflic acid system, because in the original one with the thioether, we needed to add triflic acid itself. Here, we're able to use sort of a weaker system. Then, if we want to go to the sulfone, we can either use the thioether, which probably is the best way. Again, using MCPPA, but just room temperature. Back here, previous slide, we used MCPPA at 0 degrees Celsius. And this goes all the way up to the sulfone. You can also treat the sulfoxide to the sulfone, but then why'd you make the sulfoxide? Just go in one shot. Now, this is much more active. And the way you can activate this for reactivity is just using magnesium bromide. So what happens there is reduction attacks the magnesium. It sort of gets stuck between the two oxygens. And this readily undergoes oxocarbenium formation. I'm sorry, I hate drawing metal bonds, and I know it's just like what's covalent, what's not. It's a mix because metals suck. We get something like this. Then we can do all the normal oxocarbenium chemistry after this. But this is really gentle, of course, because magnesium bromide doesn't react with anything else. It's completely inert. So you don't need to worry about any kind of conflict or something else going on with any other kind of chemistry. Unlike the other two where you had these strong electrophiles, IDCP, NIS, triflic anhydride, triflic acid, sulfones, you can get this complete reactivity and complete selectivity. The last concept I want to touch on today, and we'll come back to it at the beginning of next class, I'm just leaving it as an exercise. And next class is going to be a week and a half from now, is, let's say I have two molecules. One is benzo protected, one is acetate protected. I treat this with one equivalent of IDCP. That's going to activate the thioether ether, going to generate an oxocarbenium, and then I treat it with a nucleophile. The nucleophile I'm going to use is just isopropanol. And we'll use collidine because it's a great base on paper. In practice, it's expensive. What's the product ratio? And why? So I'm going, as a search term for you to think about this, armed and disarmed donors. So think about what kind of product ratio I expect to get from that. Like if everything is equal, it's going to be a 50-50 mixture. Half of each is going to react. But is that what happens? And it is, 9:50. I think we're done for the day. So next class, so what I'm going to do is I'm going to send out an email saying when the midterm exam is, as we discussed. I'm going to state in that email which questions from the assignments are fair game for the midterm based on what we've covered. I am going to then I think that's what I'm going to do. And then I think anything I say, go look this up, is also fair game that I've talked about in the lectures. And then, and as I said, the midterm questions are going to be slightly modified from the assignment questions. You'll have 3 hours. And next class, when we come back to this in about a week and a half, is we are going to discuss this last little bit about sulfide stuff, armed disarmed donors, and then we're going to move on to trichloroacidimidates, and then we're done glycosylations. We'll start talking about C2 azides and amides and how to play around with that, and some things about carbosugars and C glycosides, and then a little bit of enzymology of sugars and how enzymes start doing chemistry on sugars. And then we move on to some amino acid chemistry. I just want to reiterate again, the assignments are hard. They are meant to be hard. You have to apply all the stuff you've done. It's not looking stuff up. You have to sort of think about this and use the chemistry you've done, look at the protecting groups, look at the different strategies of making these things, figure out the best way to do this stuff. They take time. There is no possible way you can solve them in real time on the midterm. It is not possible to do, which is why you think about them in advance. And the reason I do it this way is because people come into this class with very different backgrounds in the chemistry, And it would be unfair of me to put together an exam, a closed book exam that would be able to evaluate everybody on a level. So, you have all the time in the world to do the assignments ahead of time, think about the questions. Contact me if you need to be pointed in a direction or a way of thinking about a specific question. I'm happy to help, because if you're able to do the questions, you've accomplished the learning outcomes of the course. So I just want to make sure that we're doing that. So please, please, please work on the assignments. Okay, I will let you guys all go. I hope you have a good rest of your day and have a really good reading week. I feel we need the reading week more this year than ever before. This is just an exhausting way to learn and an exhausting way to teach. So I'm glad it's here. Okay, take care, and I will see you guys later. I'm going to stop recording.